Hi everyone, this is Mr. Bowman and welcome to Chapter 7 of AP Statistics. In this activity, we are going to talk about the idea of sampling distributions and how that relates to samples and populations. So the first thing I want to do is pop over here to the calendar and point out that we are doing the very first thing on the calendar. And once you're finished with this video, you should try the homework problems that go along with this. Before we start, I would like to mention that if you do not have a copy of this activity, you can go to the Canvas page and go to the In-Class Notes and Activities, Chapter 7, and print them out so you can write things down as you go along. And one more thing before we get started, our goals for this activity are the following. As you can see highlighted here in yellow, we want to distinguish between a parameter and a statistic. We want to create a sampling distribution using all possible samples from a small population. We're not actually going to do that. We're going to talk about how big that would be, how many different samples that would take. We also want to distinguish among the distribution of a population, the distribution of a sample, and a sampling distribution. We've talked very much about populations versus samples throughout first semester. We are going to introduce a new type of distribution called a sampling distribution and talk about some of its properties. And then we're going to finally determine if a statistic is an unbiased estimator of a population parameter by using the sampling distribution. So without any further ado, let's get started. Suppose we wanted to find the average height of all American males aged 18 to 24 years old. That's a very large population, and clearly it would not be very practical to do a census or collect data from the entire population. If we did, we would have a measure of that population, and a measure of a population is called a parameter. Specifically, the population mean is denoted by the Greek letter mu. In question 1a, why don't you pause the video for a minute and think about a method for estimating the population mean for the heights of all American males age 18 to 24 years old. So hopefully when you thought about 1a, you said something like, I would take a random sample and calculate the sample mean and use that sample mean to estimate the population mean. The idea of using the sample mean is that it hopefully is an unbiased estimate of the population mean. So if we were to do that, take a sample and calculate the sample mean, we would get what is called a statistic. And in this case, the sample mean would be denoted by the letter X bar. So our parameters are measures of populations, statistics are measures of samples. Our textbook uses Greek letters for parameters and uses the English alphabet for statistics. A couple questions about your sample mean. Can you say that your sample mean is a good estimate for the population mean? Maybe, maybe not. Even if it's unbiased, it might not be a good estimate. How confident are you in your estimate? Well, that goes along with the first part. I don't really know. Would you expect your sample mean to vary from sample to sample? Hopefully, based on what we did way back in Chapter 4 with sampling, you would say, yes, I would expect the sample mean to vary from sample to sample. So since the sample mean is going to vary from sample to sample, that raises all kinds of questions, like how good of an estimate is our sample mean for the population mean? How much variability is there in the sample mean from sample to sample? How large should our samples be? How much confidence do we have in our value of the sample mean X bar as a predictor of the population mean mu? These are some fundamental questions that are going to get answered as we move through this chapter and later chapters. It's all an area of statistics called statistical inference, and that's what we will be spending all of second semester on. So the first thing I'd like to do is get you thinking about the difference between a population, a sample, and a sampling distribution. So to do that, we're going to start out with a very small population. says, consider a population of 20 students enrolled in an honors program at a small college. So here are 20 students numbered 1 to 20, and here is the amount they spend on textbooks. We would first like to find mu, the population mean, and then answer this question: why is it appropriate to say we can find the population parameter? Well, obviously it's appropriate to say we can find the population parameter for this population because it's small. So we add up all 20 costs or amount that students spent on textbooks, and we divide by 20, and we get a population mean of 360.25. Part B of number 2 asks you to construct a histogram for these data on your graphing calculator. So if you're going to do that, you'd have to pause the video right now and enter the 20 amount spent on textbooks. And when you do that and you make a histogram, your histogram is going to look something like this. And you can see that this distribution, or the population distribution of the amount spent on books, is roughly symmetric. And because of that, we would use the mean and the standard deviation to describe it, or we could use the mean and standard deviation to describe it. And as a reminder, you would hit stat, calc, one variable stats, tell the calculator where your data is at. Mine is in list 1, and then we would hit calculate. So even though your calculator says X bar, because it doesn't know whether or not you're talking about a sample or a population mean here, our population mean is 360.25, and our population standard deviation, sigma x, is 49.54. Very often, we do not have access to the entire population, or to gain access to the entire population would be unreasonably difficult or time-consuming or costly. So we would like to come up with another way of estimating the population mean. One way to do that would be to take a random sample of a given size, and in this case the activity asks you to take a random sample of size 5. So if you'd like to do that, you can pause the video now and do that. But I did that earlier, and my values range from about 330 to almost 450. And I got the following values when I took a random sample of size 5. 442, 378, I'm estimating where these are at in the interest of time, 419, 433, and 330. So that is a distribution of 5 sample values. If I were to calculate the sample mean, that sample mean would be considered X bar, and that sample mean turned out to be 0.4. Compare that to the population mean of 360.25, you might say that those are kind of far apart, about a difference of 40. Do I think this difference is typical, or is my sample mean unusual? And that's a tough question to answer until we look at more sample mean values. So we're going to hold off on that. Parts E and F below, we are going to have to skip those for now. It asks you to compare your value of X bar with that of 4 other classmates. And if you're watching this on a video, you can't do that. And then it asks you to make a dot plot of your sample mean with those of your 4 other classmates. We'll come back to that idea in just a minute. In the meantime, let's talk about this question, letter G. It says, discuss methods for improving your estimate of mu. So pause the video for a minute and think about how to answer that. So a common response to this question is to increase the sample size. And clearly in this case, you wouldn't have to increase the sample size very much. You go from a sample size of 5 to a sample size of 20, and ultimately you don't have a sample anymore. You have a population, and you have the population mean. But you can't always do that. But increasing the sample size is one way for improving an estimate of a population parameter, as long as we are using an unbiased method. So what I'd like to do now is I'd like to come back and address those two that we skipped over, comparing our sample mean with that of 4 other classmates. And to do that, we're going to look at a fathom demonstration. And so what you are seeing here are a whole bunch of sample means that I have collected over time, and I've collected 931 sample means from 931 different students. And here's a dot plot of those sample means. And so what you see here is the following. Right at about where that gold bar is at, there's also a blue bar, but they're so close together you can't actually see the difference between the two, is the population mean of 360.25. What you'll notice here is that the mean of all 931 sample means is also very close to that at 360.222. Now, you wouldn't try and estimate the population mean by taking 931 sample means of size 5. That just seems unreasonable. But here's the idea behind this. If you think about my sample mean of 400.4, way up there on the right-hand side, you could see that it's not a very good estimate of the population mean. However, because it was randomly selected, it doesn't seem like it would be biased. So what does this distribution tell us? Well, it tells us there's a lot of variability from sample mean to sample mean. But if we take the mean of all the sample means, yep, that's what I said, the mean of all 931 sample means, that mean is very close to the population mean, which tells us that the sample mean is an unbiased estimator of the population mean. Now you might ask, why isn't the mean of our sample mean exactly equal to 360.25? Well, it turns out that in part B of this question 3, if we wanted to find all possible samples of size 5, there would be 20 choose 5, or 15,504 samples of size 5 from this population of size 20. And that's why we did not construct the sampling distribution, because technically the sampling distribution would be all 15,504 sample means plotted on that dot plot that we just looked at. And if we had done that, the mean of all 15,504 sample means would be precisely equal to 360.25. If we do that, we have what is called a sampling distribution. And if the mean of that sampling distribution is equal to the population mean, then we have an unbiased estimator. So, we need to know about the sampling distribution, but we are not going to construct actual sampling distributions. As you can see, the amount of time that it would take would be inordinate, even for small populations like this of size 20 and small sample sizes. So, it is, however, something that we need to be familiar with. So, the sampling distribution. The sampling distribution of a statistic is the distribution of the values of a statistic from all possible samples of a given size from that population. So we looked at a partial sampling distribution from all sample means from samples of size 5. If we had wanted the entire sampling distribution, we would have to take all samples of size 5, and that would give us 15,504 sample means. But there are other sampling distributions for that population. We could take all possible samples of size 6 or 8 or 12 and so on and so forth. It's more about understanding the properties of that sampling distribution that we're interested in. So, let's talk about those properties. When the mean of any sampling distribution is the same as the population parameter, we can say the sampling distribution is an unbiased estimator of that population parameter. Notice we said the mean of any sampling distribution is the same as the population parameter. So I'm going to show you some examples in a minute here. It doesn't always have to be the population mean that we're interested in. Eventually we'll talk about population proportions, but we could talk about population standard deviations or population IQRs and so on and so forth. If our statistic is such that the mean of the sampling distribution is equal to the corresponding population parameter, we have an unbiased estimator. In that case, we can say that our one sample statistic that we took is an unbiased estimator of the corresponding population parameter. So to make sure that everybody understands this idea, we're going to do a couple of problems here. So for each of the following situations, identify the population to parameter of interest, the sample, the statistic, obtain and provide an expression for the number of samples in the sampling distribution. Okay, how much do gasoline prices vary in Chicago? To estimate, a reporter records the cost per gallon of gasoline at a random selection of 10 gas stations from the 1,250 gas stations in the city. The range in gas prices from the sample was 25 cents. The range in gas prices from the sample was 25 cents. So the population, all 1,250 gas stations in Chicago. The parameter that we're interested in, the range of prices for gas. The sample were the 10 gas stations. The statistic that we got was the sample range, and that was equal to 25 cents. Now, the parameter is the range of prices of all 1,250 stations. To be clear, the difference between the parameter and the statistic. The number of samples in the sampling distribution. Well, the number of samples in that sampling distribution, should we choose to find that, would be 1,250 choose 10, which turns out to be approximately 2.48 times 10 to the 24th. So you could see why we would not go about taking all possible samples of size 5 and then finding the mean of those sample ranges to estimate the population range. As a matter of fact, we shouldn't do that unless we know that the sample range is an unbiased estimate of the population range. And we're going to finish this activity with this idea of an unbiased estimator. Okay, so here's the idea. Below is a histogram of the population along with a few population parameters. So here's the population distribution, here's the population parameters. Just to be clear, the way this is set up, the range is this first value up here, the mean is the second value, and so on. They followed that order. And those are all population parameters. Below are some partial sampling distributions of various sample statistics. Partial sampling distributions because even a computer is not going to calculate the entire sampling distribution for us. They're just too big. So what the question is, okay, is to determine which of the sample statistics appear to be unbiased estimators. And that, what does that mean? It means the mean of the sampling distribution is equal to, in this case, approximately equal to, the corresponding population parameter. Circle the correct answers. So let's take a look here. So in A, we have part of the sampling distribution for the mean. So we have a partial sampling distribution of sample means. And the mean of our sample means is 100.021. So is the sample mean an unbiased estimator of the population mean? We need to go back up to the top and take a look at the population mean. The population mean, 100.08 approximately, is very, very close to the mean of that partial sampling distribution. So the answer to our question is, does the sample mean appear to be an unbiased estimator of the population mean? Yes. All right, let's take a look at a different partial sampling distribution. Part of the sampling distribution for the range. So a whole bunch of samples were found, a whole bunch of sample ranges were calculated, they were plotted, they make up this partial sampling distribution. The mean of this sampling or partial sampling distribution of sample ranges is 48.2 approximately. If we go back to the top, the population range is 83.9, almost 84. Are those even close to each other? Is the mean of the partial sampling distribution equal to or even close to the population range? No, it's not. So the sample range is not an unbiased estimator of the population range. So that's one that we'll avoid. We're only interested in those statistics that are unbiased estimators. So my suggestion would be you go back and you try those homework problems now, and then we'll follow that up with a little bit more activity and discussion next time we meet.